Okay, everyone, welcome to today's talk. Thank you all for being here. So first I'll tell you about our the society industry. If you're interested in joining the and memberships, £25 a year, and you get loads of perks, so alumni networking and conferences. So I'll introduce our speaker and then we'll Thomas P. Davies is the president of the Gene Technology Officer of Oxford Sigma, an R&D company that develops fusion materials technology whilst providing technical materials and regulatory support. In addition, Thomas is an honorary research professor at Bangor University and Oxford and Birmingham University. He has a PhD in materials science from Oxford. Enjoy.
Thank you for the introduction. That's great. How do you get the message? Hold on.
Not able to get it.
Okay. Yeah, thanks for the introduction. So, as I said, my name's Tom Davis. This talk today will be kind of high level on fusion, and I'll kind of contextualize it where it is today, as in right now. It will change as you play this talk next year, in 10 years' time, if you're ready. But as I said, my background is I did a PhD in fusion materials at Oxford University, my undergraduate at Birmingham University in nuclear engineering. And while I was doing my PhD, I formed a company called Oxford Sigma with my co-founder, and we do two things: we develop fusion technology for companies building fusion reactors, and secondly, we also help these companies design fusion reactors. We also do fission, but no one seems to be interested in the fission stuff we do. Everyone's more interested in fusion, and probably understand why. But today we'll give you a bit of understanding where kind of the UK is with fusion, where is the US as well. But before I do, what sort of backgrounds do people have undergraduate? So is it undergraduate, PhD, and then SAP? Sort of backgrounds is it? Mix of all. Mix of all, which means chemistry, physics, astronomy. I'm just going to put all this one. Sorry, okay, so it's science background. So there's a bit of material science at the end. My sort of research was in material science, so I'll focus on that. But the talk kind of structured, depending how long we have. So I'll briefly go with fusion energy. When I say briefly, talk about public fusion, the government-backed fusion, so the taxpayer spending money to do fusion. And then the private industry, which is solely funded by investors. And a very small amount of government money. What a fusion reactor kind of looks like in general terms, and I'll focus on some of the challenges what I face, what my company faces, and some of the people we talk about on the list. It is a biased talk. I do material science PhD, so we'll talk about materials. There are a lot of physics challenges, there's a lot of chemical challenges. For example, the majority of fusion reactors are actually a chemical plant, which moves around radioactive material, things like liquid metals. So you need complex metals from A to B, which contains radioactive hydrogen. It's actually a significant chemical problem. I'll contextualize this. I'll give a really brief background on what the narrative of fusion is. I'll say some people subscribe to this, but this is slide graph. We're probably on this slide. This is a good plot of 1,000 on the x-axis. So the idea is that the green curve is where you kind of fill this idea that fusion gets into the long-term projection of energy, producing energy on the Earth, possibly space travel, but that's another day. That's the plan. So, and the idea is to have that sustainable cycle. Most of the fuel is cerium and tritium. Cerium is basically majority of it is from seawater. The first time you exhaust that, you exhaust the majority of the Earth anyway. Tritium doesn't exist. Well, the half-life radioactive hydrogen. They actually form it by neutron bombarding lithium-6, and there's some proportion lithium-6 and F as well. There's a bit of a toy with electrical batteries, but I can really high level contextualize. But what we really talk about fusion, the process that we use atoms together. The sun's a very good example. The best way to describe what we're trying to do on Earth is put that into a box. The minute temperature 10 times greater, because that confines itself by its own gravitational pull. So I didn't have that electron on Earth, so we have to define it other ways. The most common ways that is confinement or inertial confinement by lasers or explosion. Things like a weapon is exactly the same as well. I'm really going to talk about one fuel cycle. I think it's a bit more addressed. So if you do know about atomic fusion, there's other types of fusion you can do, at least in theory. The sun does hydrogen fusion, which takes a very long time to do. So the easiest way to do fusion on Earth so far is using H2, so deuterium, heavy isotope of hydrogen, and then H3, which is tritium, the radioactive version of hydrogen. And you fuse it under extreme temperatures, generally about 10 million Kelvin, and then you end up having a helium atom and a neutron, and spoiler, neutrons all the bombs. That ruins all the reactor vessel itself. There are some other reactions that are following DD. DD, you can do material, DU3. There's no new going out. There's a lot of new. So there's big companies trying to use the DU3 fuel cycle. You haven't solved the DU3 problem yet, but where to find it? Technically, tritium decays naturally to DU3, but it's hard to get the tritium in the first place. So we mainly deal with DT fuel cycle. So that's where the common problems are. And the line here is your essentially your reaction rate. So the higher the line, the more reaction you're going to have of a fusion reaction. And this is a function of so what access temperature of billions of Kelvin. So you want to go sort of the closest side on the y-axis, highest y-axis, the temperature as possible. The DT always wins. So you end up doing a DT fuel cycle. Contextualize it in terms of, I just came from so today was a conference at Science Museum hosted by the UK Atomic Energy Authority, government's National Lab for Fusion. And it's the idea of, it's called Fusion 22. It was the first time for a long time where policymakers, investment companies, private fusion companies.
There's an issue with the slides.
Oh, yeah, what is it?
Could you like reshare the screen? Yeah.
Is it not resharing?
I don't see this. Yeah. For some reason, it's sharing the room. Could you share the folder?
Are they seeing it now?
Yeah, that's better.
Sorry.
No, is it working now?
Yeah, it's perfect. Thank you.
Cool. You haven't really missed you on two. So the context, so the Fusion 20 conference just came from it, but it's the first time government, private companies, policymakers, investors, sort of large scale oil and gas companies, all come into a room discussing how fusion could be, in this case, commercialized. And the idea behind this is many projections that are all really correct in many ways, but where fusion fits in the landscape, if you know, this depends on what you mean by this date here. So that looks like 2030s, 2040s. Depending on which company you talk to, they say that when they're going to have fusion as an actual generation. So that could move. If you're the public fusion side in Europe, for example, your first coming on start reactor 2016. So there's a private fusion saying that's too long. So they want to start in the 2030s. There's some challenges with that, but the idea about fusion is no CO2 emission of fusion of power. But as you can see, the green bar here, this is actually still CO2. But do you know where that CO2 comes from? It's interactive, guys, by the way. So so concrete, steel, decarbonizing steel and concrete is actually really challenging. And you can probably see it the like water reactor fission. Reactor fusion actually needs more concrete and more steel than a pressure water reactor, for example. But yeah, actually decarbonizing those technologies has not been proven yet. So what they can just look at the photovoltaic with they actually consume a lot more material per watt produced. So the running joke fusion is still going on. This is actually years away. Who's had that? Fusion's always 30 years away. And was it how long did you go on for?
It's the early 70s probably.
That actually derives from 1976. So where it actually comes from is a report from at the time of the Department of Energy Research and Development Administration, now renamed Department of Energy in the US. So they did this projection, not black line, it doesn't exist, right? In this case, they projected that in 1976. If you had the maximum effort to get fusion as electrical energy source on the grid, with particular budgets, it would achieve in 1990. 1993, different accelerator, aggressive and moderate. If you look at the moderate, that's about 30 years away. Then they also have 1970 level effort, aka fusion never. And obviously, it plots on the actual project. It will always be 30 years away. But that's where that joke derives from. It's changed. We'll see. This is more conceptualized there, but we don't have to decarbonize the grid. It's just more about politics and policy. And this is where Fusion tries to position itself. I saw it today at Fusion 22 conference, it's trying to position itself as this being carbon tackling of the 2050 net zero targets. I'll say that's debatable. By the time Fusion actually becomes available for electricity production, people disagree. Story from France, a really good case study. So the French in 1974 decided to go all nuclear, based on the oil crisis at that time, to be more energy secure, which sounds a good idea today. So they decided that. So obviously you got the nuclear generation, it's a bunch of years, and you can actually see the green curve going up, and that's displacing the oil and gas and coal rather than nuclear power coming up. But France are said to reduce their nuclear production, but that's because the renewables are increasing. So also their CO2 emission as per GDP capita is the lowest. So at the point this is a graph of Germany versus France. CO2 emissions in 2016. I guess why they on average generate more CO2 in France. Chart I'm going to show next. France is much nuclear, Germany is still with gas. Obviously, slightly changed. I got the inside many a year ago as a different emphasis today than a year ago. The idea of fusion, at least if they can actually make commercial electricity production, is to displace a lot of oil and gas. I don't think it will be displacing fusion energy anytime soon. I don't think it should do anyway. They should not be competing. Displacing all the coal and gas. So, I don't know what fusion energy is, and I'll split it into private because they are two different things going on. Anyone seen what a fusion reactor looks like? So I'm only going to talk about one type. That's a tokamak-based reactor. It's a Russian acronym. Essentially a residual, a torus, a naturally confined torus. Essentially, you're going to get tokamak as an acronym. The idea behind this is I mentioned that the sun confines its own fusion reactor as a plasma by the gravitational pull. It's big enough for it to crush itself to a temperature high enough for hydrogen 1. You don't have that for that. So there's two ways to do it, two major ways. One is magnetic confinement, which we'll talk about today, spaces, and all those other ways. But this one is magnetic confinement. So you're going to basically heating your plasma to about 100 million degrees or so, and you suspend it in a magnetic field. Plasma is charged, so you can suspend it so it wouldn't touch the walls, maybe. It does touch the walls. And there are some conditions where it actually rips holes in the walls. And in the center, there's a solenoid, so you imagine a transformer. It's a very transformer idea. You have one wall winding, solenoid, induces a current here, which is in toil direction. That'll get your plasma up to about a couple million degrees centigrade. And then you've got the toroidal field, blue, and that confines the twist magnet to the magnetic field, which if you ever didn't have them, the plasma would just spin off some stable and just want to be a plasma state. So you can find it by having the blue coils, and then you also find further coil and gives this beautiful magnetic field resulting, which can spin and traps the plasma itself. So it's never ending loop. It's not perfect. That's the reason diagram. There's actually a lot of correction coils trying to correct the magnetic field. It's not a magnetic field. You do get plasma spin off into the sides. This is put in the entire pelvic fusion on one slide, which is this service. There's a lot what's gone on in the past. I'll talk about what the main 3 steps are. The narrative. You get JET. So JET is called Joint European Taurus. It's in Oxfordshire. It's in a place called UK Atomic Energy Authority on the side of Culham, which used to be considered Culham Science for Energy. Oh, it's hard. So JET's been going on. 1984. That's actually on 2022 now. It's still going on. It's nearly decommissioned. It's about to turn off in the coming weeks and days. It's finished the mission. So its mission, JET, was at the time in the 1980s. So the JET was done in the 70s based upon the results from Russians in the in the 70s and 60s. And this was the idea of trying to actually have real deuterium tritium fuel, which is the only reactor in the world that does it. It's been one of the American failed mission, but it's now finished. This is the last form of the real fusion. Due to turn off, there is a successor. And the question is, who's going to clean up JET? Because it is very active. And it's a European project. Yeah, we are. Terrible. There is part negotiation of Brexit down to the part. It's a fairly expensive cleanup project. Anyway, so moving on, after JET, there was ITER, used to stand for something, but now it's just an acronym. This was the consolidation, and it started in the 90s. So a lot of technology was late 90s. It was frozen in time. That's what ITER is. It's an accumulation of the entire world's effort on making fusion power. It doesn't produce electricity, but it's designed to produce more power than it produces. And it's combining all the technology which is being developed independently around the world, bringing it together. And the countries which are involved is essentially European Union, don't ask that for since that's still an ongoing problem in that part. You've got America, you've got Russia, you've got India, you've got China, Japan, South Korea, and it's the only project which is immune to the Ukrainian invasion. So Russia is still delivering. And they have a choice. It's these things that Russia will. But as part of the negotiation, it's together. It's a cross politics. It's a truly international program. It's been delayed by negotiating that program. You asked the question about if you develop, for example, the magnet system, a lot of money in magnets, it's billions of dollars in magnets. Who gets the IP? Intellectual property. If you have all these countries, so they managed to be able and give multiple countries to build magnets independently when they're bringing them together, and they should all work in some way. Of course, there is. And then post that, the narrative, at least in Europe, the Eurofusion program, which is the European program, which we're kind of part of. Energy demonstration, it says 2040, it used to be 2050, now it's 2060, depending on which you ask. And that's the idea of producing actual electricity on the grid from fusion. Still, they're called demo reactors. Every country has a demo reactor design. So European has this just EU demo. America doesn't have one, they've got a different route. China have one, South Korea have one, Japan have one. India has one as well. It's designed, it's paper design, it's not actually built right now. But these have been going on since the 19th. So March 2009, that's where the site of it is. It's in Cadarache, South France, the lovely bit of the countryside. They flattened the land, and it's not actually the orientation is if you look the other side of this photograph, as well the weapons of the design and manufacturing in France. So it's a new site, just And then all the test grounds to this side. So there's a lot of skills still over. As you can see, it looks flat. This is just over 1,000 years later. And you've got, so this is Peter, on there, but this is the top right there, but this is how the top right is the system one. We've got the construction building. There's a building next to it, which is the assembly hall, and that's built to essentially assemble the reactor that we move slowly on top of it. And then the wall, it's a very large structure. And then you've got various auxiliary systems that you build around it. And again, the idea of this is going to be producing more power than it consumes. We're not producing electricity, we're just producing electricity. There was no plan forever to be producing electricity. But the idea is a demonstration, the integration of all the technologies coming together around the world. This is another photo of 2021. See it coming together and assembly walls moved over. So that's what it's going to be. Here's all the rings of the confinement vessel, the power grid coming in from that. It will draw gigawatts of the grid, store the power, power of the magnetic systems, which is superconducting. And then latest photo was made 2000 May this year. So they started to assemble that storage chip. This is one of the rings. So this is made out of stainless steel. And they're going to assemble them. They've got a bit more now since the photo we have this. But one thing I didn't tell you was stuck. So it looks very nice. But they get stuck. You can see the central column support, that's just the steel structure support. And inside there will be a superconducting magnet. It'll be cooled to 4 Kelvin by helium. And then you can see the sort of the shape of the vacuum vessel. So there'll be a oil field magnet around here. You sorted it. Those are wound on site because there's not a ship big enough around the world. So they wind them on site. That's made out of iron tin. So it uses a substantial amount of kilometers. It's in the kilometer scale how much superconducting magnets they produce. So that's the Scientific Public Fusion Program. If you ask anyone in Europe and in the UK until 2019, what happened in 2019? So we had Boris Johnson got into government. That was the story. I was on the UK Atomic Energy Authority, which is the UK's national lab, not actually on site, doing my PhD. Boris just got to power. It's number 10. I looked at the window what I just walked out. And I went, oh, there's Boris. No idea what the context was. And then a couple of hours later, there was a press conference. So what they announced was a project from UK called the Spherical Top Map for Energy Reduction, also known as STEP. So what STEP is, it's essentially an ambitious program. It's very ambitious. To deliver a prototype fusion plant by 2040 and a pathway to viable fusion. Led by UK Atomic Energy Authority. And I left off the number, but they got £220 million from government based upon that announcement Boris made. It was a pet project for Boris. Before, it was a science powerhouse, but a flagship project post-Brexit. And someone was coming to put fusion in front of him. And funded this program. Big on emphasis. And we're a recipient of some of that money for contracts and work. This is their sort of best design I've seen so far for what's that look like. It's meant to be a demonstration fusion device. They did the sighting. I don't know if you've read any of this, anyone heard of that before? There was a site location competition where to put it. They were not going to put it on the nuclear site, already existing. That's a political nightmare. Whether it should be on the nuclear site or not, that's a problem for the future. Right now, that's a political agenda. So 5 sites gave their locations, and at the Conservative conference, it was announced where it was going to be. Particularly small, which was the business secretary. They actually pushed the announcement a bit quicker out than expected, because I don't know if you looked at the Conservative conference, it didn't go that. So this was a positive news story which got swamped by the negative news press. So they actually chose West Bath. So anyone been to West Bath? Anyone know where West Bath really is? So what's actually there is a village, but next door to it's a coal-fired power station, and you get energy. Still produces coal. It will run off next year. So they announced it after a competition. Whether it's suitable or not, it's a different story. But here is the site. So remember, this is going to be a flagship program from the UK government. Assuming they fund it all the way through, there will be net 20 billion. Give or take. If this year was. You don't want to ask £100 billion government today. It's not exactly the best thing to do. But you can see this coal-fired power station. Here's the coal-fired power station. It's a gas turbine. This is a coal ash bit. And the site actually goes on here. You can see the river Trent. So this is where it's next. So, and a few reasons why this was chosen. A, it's not a nuclear site. B, it has a grid for 400 kV connection, so you can draw power from the grid to produce the fusion reactor. And then there's a train line, so you can deliver a lot of goods. And then there's also the cooling. So there's a nice train. There's a reasonable water flow which will cool you down. So that's essentially what the UK government doing today. So at the Fusion 22 conference today, UKA were the lead of the conference, and the idea was set is going to be the step to take to fusion. Doesn't really bring on, does it? It's taking a little bit. And the idea is that's going to be the platform for private fusion, which I'll talk about in a minute. Question is, if you had a company in the UK who was developing very top reactor type technology, they got investment of over 175 billion pounds already today from private investors, does that compete with what UK government is doing? Bit of a grey area. I'll make that as a comment because in a minute it's all private, and I'll compare it to the US. So the UK historically has always got involved from a government perspective into projects. UK government's always had a hand generally. The US doesn't normally do this. I'll show you exactly where that is. So in parallel to all this happening, the United States, we work on the United States. It all started off in 2018, which is not very far ago. When Trump was in power, there was a new law which was called Nuclear Energy Innovation and Modernization Act. What it essentially did, fusion, it put it on the radar of Congress that fusion is A, something, and B, commercialized, and C, it could be a electrical production, some sort of energy power station. There was no, in the law, there was no, it was not clear where fusion sits, who regulates fusion. The law says very clear, it's regulated by the Nuclear Regulatory Commission, which is the nuclear authorities. And that's fine. So now we know exactly what that is. And what regulatory regime that looks like is being debated today. In parallel to all that, we've got multiple funding programs. So there's 4 different funding programs for different reasons for fusion and energy science in general. But a lot of fusion private companies spin out from down paper the smart marine funding grants. So a lot of the private US companies are actually starting on those grants, and they're about $1 to $5 million each. And from that, you see investment from the private industry, and you can raise. So I'll show you the minimum numbers, but some very large numbers. So Distributed Mind STEP UK project is £220 million. Let's keep in that mind. So in parallel to this, there's a little bit we want to reduce money, which is actually this is £2 billion. This is the most important thing to know. If you don't take anything away, so do you know how SpaceX became a company and how it's profitable? So so basically NASA did a competition called COTS, so NASA's Commercial Transportation Services, and this was drawn up in 2005, 2006. And the idea was, how do you create a space industry when there's no industry? There's no customers, there's no market, there's no revenue. So the government took the risk and said, well, rather than NASA sending astronauts to space with their own vessels to get the private fusion, private space industry to do that. So you had SpaceX formed, Blue Origin formed, and they competed against the government contract. Eventually, SpaceX won, and they essentially got a 20-year contract with the government to send astronauts in their space shuttle. Now, that exact same program has been copied for fusion, and it's just started. The law has been laid down in Congress very slowly over time. So the first one is called a public-private partnership cost-share program. Americans acronyms are yeah, that's what I heard about today at the conference. So the PPP program, currently they've got a call open, first call, and they've given $50 million, which is modest in this regard, but it's the start of the application process. So they'll give 3 to 5 winners of the program. You submit in December this year, and the idea is you have at least two good winners, with 2 fusion companies wanting to produce a fusion reactor. Which is a good idea. But and then you've got 3 other ones about supporting technologies as well. But don't be surprised that 50 mil isn't a lot of money. It will turn into a 10-20-year funding program, which will be some up in the billions. That's how America do it. So America is very good at taking a sort of entrepreneurship style and then bringing it out to an industry. And it's done through these programs. It's been very successful so far. So we'll probably see the same thing with fusion. All the hallmarks are there. All the senators and the congressmen are all for it. There's no one pushing against. It's all bipartisan. I mean, you know, it's bipartisan. It's all going to go through. So that's the start. Oh, and then there's a picture. That was the White House summit in March, and they basically outlined the sectors of energy, set out the 10-year plan, commercial fusion energy, which is quite ambitious, I would say. So that's going to preempt the private industry. So that's what the US are doing right now. UK are taking the approach that the UK Atomic Energy Authority, being the government national lab, is going to be leading this power reduction sector program. In the US, there's no such thing like that in the US. The US is here's the money for private companies. You show us what the best options are, and then we'll give you the contract to produce engines. It's a very different mindset. So where the private fusion industry sits. So really good way to look at where they are is there's a thing with Fusion Industry Association. It's mainly based out of DC. It's a lobby firm essentially for policy fusion laws, and reels parts of it. But they do a summary every year. They start with this 2021 summary of just the industry as a whole of private. You can see they have about 1.8 billion of private investment. And this is all a little bit 85 million for government, but you can ignore some of that. So about 1.7, 1.8 billion dollars have been partly invested as venture capitalists through seed money. There's a lot of rich, there's a lot of rich companies out there. And the number of private fusion companies, this is defined as companies who want to produce electricity to match their revenue. Basically, ever since 2008, 2009, it's increased quite a bit. Most of them in the US, over 90% of them in the US. There's a few in the UK. But since that announcement, that was August. That was August 2021, November of that year. Needle Energy, a company that we know, based in Seattle, secured 2.2 billion. That's when you beat the total 1.8 billion of the entire fusion industry before that. Most of that money is Silicon Valley. So they've got 2.2 billion promised to them to produce their fusion reactor design, which is not the top of that. It's going completely different. They have very good their website. It's called a grass field configuration. The idea is you shoot plasmas into the center, then it expands out and expansion. That's called fusion. But they've got 2.2 billion. Since then, another company, Commonwealth Fusion Systems, from MIT, raised 1.8 billion. That was in December last year. And I'll show you some structure for Commonwealth Fusion Systems. They're trailblazing it. They are essentially building a jet device that will find some of the superconductors, which on all counts will probably do more energy output All the history and all the research tells you that's eventually going to happen. They now have the money to do it. That's the difference. So this was only December. Before that, most people didn't take it seriously. The US government have now had to take it seriously because they have more money than what the US government gives to the fusion. And I think a good fraction of that money came from the gas, ENI, which is the Italian oil and gas fund. Another one, General Fusion. They were a Canadian company, been around since the mid 2000s. They fundraised fundraising is a series, like a lot of fundraisers, ABC, $100 million US. This was announced in November of last year. Managed to build a demonstration reactor device on UK atomic energy site in Cullen in Oxfordshire. So there will be a private company in Oxfordshire building their sort of demonstration sites. It's not going to do fusion, it's going to do serum plasma, but it's a consolidation of all technology they've done independently. They put it together. I should show you a picture. I haven't got the General Fusion. Have you ever seen the compression of hammers in a fusion reactor? That's General Fusion's approach. They shoot a plasma into basically a spherical chamber, which is a vacuum, and at the same time you sustain that plasma in the sense of finding it with something, and then you compress spinning liquid metal, which is now spinning around the chamber. You compress it using pneumatic hammers for steam, and the compression of the liquid compresses the fuel, which is tritium, to a temperature high enough to fuse. So, has it been shown? And then there's another one. This Australian. I've got different reaction. Both on boron. This fuel cycle, you have also basically hydrogen and oil levels pretty abundant. This is using basic fusion. They're a new spin out of the latest. They got $22 million fundraise for the beginning. And the whole point about this is there was a new report in 2022, August. Now it's also money for $8 billion. So there was been an increase of about $3 billion since then of private, all pure private money. So when I said step was £220 billion, the majority of the cash is actually a lot of the activities. There's two graphs here. So this one's some of the companies, what's their goal, energy generation. There's a few specifications. This one's an interesting one. So when the first fusion power plant deliver electricity to the grid, it's a self-fulfilling prophecy. So they're always going to shoot what their commercial team's been said. But obviously most of this is not scale, but you can see the graph. 2030, so basically very best. If you ask this by the end of the decade and do the same poll, is it going to be the same? That's shifted slowly. If you look hard enough, from way back 5 years ago, companies have said they're going to have fusion power on the grid 29, 28. Some companies can say 25. They're now saying prices. I've seen one spotted saying 24, hidden, buried in their news press. It's all, the point is, it's all shifting. Yes.
I have a question. Explain what's the medical use of fusion? Is it radiation source?
It's actually make money. So it does work. So what medical is a good example. There's a company called Shine based in the US. They essentially, we can all make fusion. It's pretty easy to do fusion now, DT fusion. We find enough energy, we do it. The hardest part is to get more energy out. So my stuff, they don't want the energy out. So you can actually have essentially you have a window of deuterium gas. If you fire really high charge particles of tritium into it, you can cause confuse. And it will give off a neutron beam of neutron fusion. That then hits the uranium target. Essentially that uranium target then bombards the neutron multiplier. In this case, it's not the uranium's not making energy. The neutrons then go into a reactor of basically molybdenum, which makes your med device to technetium-99. Very, very efficient way to take technetium-99 and you ship that off to hospitals. That's the money generator. So the only companies doing that today in the world is Shine, based in Wisconsin, spin out from Wisconsin University, and they're doing that. So that's a really good way. You're essentially not using a nuclear reactor to make money most of it now. you're having essentially subcritical uranium uranium lithium mass, and you bombard it with a controlled pulse source, so you can time the neutron source on. You have full control of that uranium. So it's a good question. So obviously some companies think you have to, but the only one which actually has a large device this time. Yeah, so just watch that graph. That's my prediction. I'm not building a fusion reactor, by the way, so we just try to solve some of the problems. So in terms of the industry as a whole, private fusion industry, on the left, pretty much most of the private companies are pursuing some sort of commercial entity fusion. Let's put this in, I think I made this slide in September. It does some used to be existing in my mind. Some companies disappeared in the sense that they determined they figured out that technology doesn't actually work. The big ones in the top, so Commonwealth Fusion Systems mission of 1 billion, Helion has 2 billion. Top Energy is the UK company, they have 175 million. First Up Fusion is also based on spin out of University. They have 2 million pounds, like that. And they have various other companies. They are happy to they used to be there. The fusion supply chain. This is just in the Fusion Industry Association, so it's very small grass of people. And there's a fair amount of companies. Interesting on this list, if you look into it, a lot of them are law firms, a few law firms in the middle. But look, top right, doing all that they make submarine reactors for the US Navy, and they also build 1,000 plants, which are nuclear reactors. They're an enormous American company. So they're hanging around, watching what's going on in the process. So they'll be the ultimate people, those sort of companies, be the ones actually constructing projects, at least in the US. Who's going to operate one? Top of the question, no one actually knows. But who will take on the liability and the risks to actually operate a fusion power station? That hasn't been solved yet. I predict to be an oil and gas company. I think about when it's come online in the 40s. What the oil and gas needs to do, decarbonize is one way of doing it. So why is there a private industry? It all kind of derives a few things. One is technological advancements. Remember, ETA was locked in at 90s technology. Since the 90s technology, there's been some advancements. The key ones to get across high temperature superconductors, which keeps a sustainable magnetic field high enough to find plasma. That's a high temperature superconductors. We're talking 70 Kelvin. That's at least the start state, that's the management temperatures. You actually only operate at 4 Kelvin. They're much better. Superconductor magnets are 4 Kelvin. So all in the view, but that enables physically smaller reactors, at least in theory. So this is the point of time scale. Usually you use DC. So the easiest time scale, by the way, when you get a turn on, this is the date. 2025, 2026. This has to be reflected over the days yet. So probably like 25, 26, 27, you see first the plasma, which is not fusion plasmas. Fusion plasmas will start. At least 2035, so we actually see real fusion, and that's when we know if it actually works as a science mission. And that's what in parallel is that you have a program. If you actually look at the program, the time scale they're considering is 2060. So in parallel to this, you've got these advancements in technology which each and then will do not include. So hydrogen superconductors is the key one in this, which has convinced enough private investors to give money to companies. And that's what's happened. One of them is Commonwealth Fusion Systems. They want to receive 1.8 billion for oil and gas, spin out of MIT. Their sort of pathway, their commercial pathway, this is what they look like. They Albert's CMOD was a top map device sponsored by Top Energy, the MIT, Southwest Down. Commonwealth was built a basically a magnet of A2 scale. They're going to do a reactor called Spark, which is essentially a jet-like reactor with high temperature superconductors, and that's the regime you can probably be pretty confident use cubic one, which is more energy happening, just stop electricity. Then they have early 2030s, and they have this development park, which hasn't really been developed, but that's their pathway. So their fundraising, 1.8 billion, is solely aimed at building site. And now all they want to do, the main goal of CPS is to demonstrate fusion can be possible. And all that means is more energy happening. And all that really means is you basically sum up the energy going into the plasma, you sum up the energy coming out. Forget all the inefficiencies, all the conversions. That's what people are actually focusing on. So, lots of pictures of it. This is March 22. So, since they've fundraised, this is somewhere in Massachusetts, just west of Boston. They've got their magnet winding all being built in the background. In front of this is where Spark is going to be constructed. Here's the pit in West Park, go in the centre. The top not going to fit. Here's the latest photo. I managed to find in June. So you can see here's the background. You see the winding square. The reactor's going to sit. They were very proud of this picture, saying we're doing those developments. I think just one and saying, all the build. That's not my very difficult to show. But I mean, they're cool, so they will build it. They will, whether it's going to be on time, which I see. That's one company. I'm going to go for another company, and this is the Umbro one spin out from. It's actually spin out from UK Atomic Energy Authority in 2008. It's called Atomic Energy. This is actually slightly out of date. Roadmap of their production package was very similar to this today. So I mentioned they got nice and superconductors, and then they also have this Atomic that I'm really talking about. It's basically a Atomic device. They got a call out. That's the sort of shape it's going to be cross section. They're operating today. They're only active with ST40, and it's operating DD plasmas. They want to build ST, it's now called STHS, but STF bombs to demonstrate fusion power. Again, just heat, and then the idea of commercial demonstration of STP1, so it's very top of my head one. It's not in around 2030s. So time frame. This is what their stock looks like. It's in Milton Park, which is just essentially about 6-7 miles south from UK Atomic Energy Authority, the Jets. So they are going to talk device here to the side, which they operate daily. So they have a lot of skills and understanding of fusion. Now, this is an somewhat organized, it's real by a guy there, Southern. He's a CEO of CTP, another private fusion company based in Seattle. You can organize the community based on technology, and you start off at the top, the type of fusion you want to do, how is it going to be continuous operation or pulse operation, you need a compression of the fusion fuel, magnet compression, but for non-magnet confinement, you might have the compression, plasma compression, laser compression, projectile compression, which is quite fast enough for force fusion, and then different ways of combining it. And then you can fuel type, DC, for example, and then you can start slightly organizing the industry. The conventional way is here, so jet, this is the DPP reactor in California. And then you've got CFS, which is using high fuel magnets, we'll go down the high fuel side. Atomic Energy, so Atomic Magnets, the Sicilian. General Fusion is good another one, and then Canadian, but they do Britain. And you've got goes on. But the outliers, by the way, if you're interested about, this is all traditional, very well known physics. We know how to do this. All programs have been since the 60s. These guys over here, which are the interesting ones, these are the outliers. They're to completely different type of fusion. There's no magnets. So you can set pitch. So you end up having basically a rod about this long. You fill it with gas, you throw a current down of megawatts, and it basically collapses the rod under a tip. Field reciprocity force fusion has been shown before to make it actually very difficult, but the amount of money required to build facilities is much less than what it's top might be. So the sort of barrier to this commercial market seems somewhat easier than sort of macro device, but the barrier to physics can actually improve itself as well. So you get that over here. There's not every company doing this, just some, but it gives you an idea. It's a bit of the message I'm trying to provide is busy, lots of things going on. This didn't exist 15 years ago, 10 years ago. It was all done by the local programs, and that was it. And there's been a fair amount of change since then. A lot of it is the technological development. A lot of it's spun off from high temperature superconductors, and then the other guys are then thinking of it different. Much more high risk, but maybe higher payoff. So, conscious of time.
Whereabouts are you? It is quarter past, so anytime you can take questions. So if you just keep in mind some time for questions.
You can take questions if you like. I can go on and talk more about issues. Or would you like material science, or would you like questions? Go on. Right. Take a top map and take it like this. What does top map look like? This is easy, but I'll give you an idea scale. This is first of all, this is what the first plasma sees. I'm going to talk about what material is going to be made out in a minute and how it was destroyed. Got the diverse exhaust gas, so you make helium, you look a little bit. Probably this person, you can see the scale. This is the person. It's not, you saw pictures of it anyway. Put the solenoid in it. The central solenoid. By the way, the cost of the central solenoid for the reactor plant is about 40%. Just the raw cost. That solenoid is enormously expensive. You don't want to fail.
So why is it so expensive? It's so simple.
No, it's superconductor, it's not cheap. And there's a lot of superconducting material in that column. You need basically what you need is you see the distance from the center here to the center of that. You need that Tesla to be as high as possible. To get as high as possible, you need everything's the other way is very much basically shrink this space. There's a complex of problems when you do that. Your heat fluxes go up because it's per unit area, so we have this area. We've got some cooling plates. I told you those correction field coils. So there was a lot of correction field coils to make the plasma more stable. You've got the toroidal field coils on top, which are weak things and the support structure to hold them up. And then you toroidal field coils, which are the ones see in here, one massive magnets and superconducting magnets. Even called four then you got the thermal shield, the power pumps attached as well. But this is all in the vacuum. It takes weeks for it to go down to vacuum. So if you do have a lot of vacuum, meaning have air ingress, it takes 4 weeks for it to go back down to the conditions you need. The price that, so this is a project sheet, so the price that, see it big. That's the major sort of components of fusion reactor. I'll talk about one problem, which is diverse. So this is again a cross section. So a plasma makes helium. If you get rid of it, it's a poison for the plasma. So you can check the magnetic fields in such a way that it scrape off there around the edge. Or something like that will fall out to the edge and you scrape it away. It's got to go somewhere. So you've got to think about diverse. And think that diverse the plasma 2 times. So there's a lot of heat flux. So plasma do touch water. So this is sort of the heat flux you're expecting on a diverse region here. So you see the tiles is about 10 megawatts per meter on average. Sometimes a bit less, 5 under active scenarios go to a gigawatt per meter square. Now, 10 megawatts, that's steady state. So what is equivalent to 10 megawatts per meter square? It's approximately the same as the Apollo re-entry telescope. Heat flux, that was a sacrificial material designed to blow up that rate. We don't want that fusion reactor, we want this thing for that. So what do we use? Anyone know what we use? Tungsten. I'll tell you why tungsten. It's not like the easiest.
I don't control radiation.
I wouldn't say it's radiation tolerant. There isn't an option. So this is what jet looks like. Superimposed colours. Things. There is a brilliant spiral, which is green, using metallic brilliant. That's actually been ruled out for commercial fusion. That's just it was just again, ITER was designed in the 90s, fixed, never changed. Very reasons like that. Since then, we know a lot more, and actually it's easy to have tungsten. The tungsten, you see the houses, diverse fusion. This is what it looks like. Tons of tungsten. So they don't know much about tungsten. as a material. Yeah, but it's not very cheap, it's not accurate, but it's abundant but not mindful. There's not much demand for it. So now we know the conditions of the diverse region. Roughly works that like that. So you can work that like two ways. Melting point of an element, we say 40,000 Kelvin. And then you also want a thermal conductivity of approximately greater than 50 watts per Kelvin. So that leaves you easy on the levels. You can probably eliminate a few already. Cost availability, so electric hydrogen, molybdenum, tungsten, carbon, and chromium. So most fusion reactors up to date since 1950 carbon tiles, very easy, very cheap, actually one of the best first walls of plastic control. The thing about carbon, it lights hydrogen, makes hydrocarbons. So when you have a fuel which is tritium, which is hydrogen, it's no different. A lot of the tritium is lost in the walls, which is unacceptable from a regulatory standpoint, from a safety standpoint, but also from a power balance with a losing the fuel. So, and then you also have a thing called beyond fusion, but if you bombard lithium, you end up producing technetium 99, not 97 M, which is the medical one, but just 99. That half-life is 10,000 years. And then niobium produces niobium, which is thousands of years. The idea in fusion is to try to be a bit cleaner in its waste management. So the community is made a conscious decision, still debated today, to remove those, even though the lithium is actually the best option. But it's removed, you can't use it because of radioactivity. You're left with chromium, tungsten, and carbon. I mentioned carbon's gone because of hydrogen, and also kind of expect 6,000 years after that's manageable. And then you've got one last thing is there was radiation damage. You've got chromium and tungsten left, but then unfortunately chromium's gone because if you heat up chromium, pure chromium tiles, 800 degrees centigrade, 900 degrees centigrade, they start reforming their crystal structure. They end up becoming very useful material. So you get with solid choice. Tungsten is not an easy material to work with. Give you an idea where it's kind of looks like. So that tile, the general design of them is you have some sort of inlet temperature, but this is helium in this case. And you have a pipe of some steel, and then you have essentially tungsten tiles as a copper into there for heat transfer, and also tungsten has a heat expansion coefficient, which is 4 times bigger than iron. So if you have that direct iron and tungsten trying to manufacture that, it's actually one of the biggest challenges. The differences in heat expansion because of the plant. So actually copper is very malleable, copper is good into lead. It's also got high level of activity. That's a general idea. It comes out a bit hotter at the end. It's just tons to look at, by the way. So you've got hundreds and hundreds of these types. They're just very simple copper tube. Slightly diameter for sort of a bit of transfer. Problems with tungsten, right? So, one of the last 2 slides I'll present, and then we can go for questions. So, when you dig up tungsten, it comes up. So, this is a graphic by tungsten fusion energy by research Mark Gilbert. So, you start with tungsten. So, this is the proportionality you dig up from the ground. Tungsten 180, 182, 183, 184, 186, and the colours are represented to its percentages. It's like it's the 20%, 20%. Now, that's fine. As soon as you put neutrons through it, what do neutrons do in the transmuting? So they'll go, this is a chart of nuclides, so the number of neutrons, the number of protons. So we're going to go neutron radiation, it has undergoes nuclear reactions, and it becomes other things. So this is a time after the play, I'll repeat it. You can see what's going to happen there. So as soon as you've got a lot of fusion neutrons as a power station configuration. Oh, cannot really. What actually it's just a little over this. Okay, it doesn't. So you can imagine as you throw neutrons, if you throw a neutron in, the neutron goes up that way. But when it goes decay, it's stable. If it's an alpha decay, it'll go down this way. If it's a beta minus, it'll go this way. Beta plus will go this way. Around. We're going to go over that. But continuing neutron radiation. So you don't actually see tungsten. Tungsten then becomes rhenium, and the rhenium itself transmutes from osmium, which goes at one. Some of the osmium becomes iridium, and some becomes platinum. And then also you get tungsten, which cases tungsten, and eventually you bombard tungsten into platinum. You look having an alloy which is starts off 100% tungsten, 2 years of operation, 2 3 years of operation, then having tungsten, about 5% rhenium, 1% osmium, 1% tungsten, and then some sprinkles of platinum, really platinum. Find out any information on those systems really good because no one has any idea how those elements fit into tungsten. A good friend at Oxford when I did my PhD, I was building insight. So this is real tungsten in neutron radiation fission reactor, and this is atom photography, so looking at the atomic scale, and basically chemically identifies all the atoms in the sample in 3D space. So you see the scale apart from that. The only thing you really need to know is the blue is tungsten, so it's kind of uniform. The readings produced with tungsten, it actually moves and diffuses and forms these very hard precipitate. So what that tells you is that tungsten radium doesn't want to be together; they're not soluble in an alloy. And then bombard with rhenium, it actually converts to osmium. And osmium sits in. This was first found here in the research in Oxford, and essentially osmium is only concentrated in the center of rhenium. What it does is it ejects out rhenium. It's going to get very hard precipitates. These are really small scale precipitates. What they end up doing is making alloy fail, tungsten fails, cracked horsepower, and it's made use of these sort of processes. I'll make one last thing. A little while there, but so how radioactive does it get? So the tungsten tile is around a long scale, and a fusion reactor after 5 years of operation. This is also how radioactive it is per kilogram. And you look at the black line, and it took 1 year. 1 year mark. So how much tungsten is there in a fusion reactor? This type scale. I worked it out, so 3.6 times 10 to the power 6. So 6 negative. 3,000 tons of you can work out what radioactive is. Then you compare it. So there's a comparison with activity. You've got water, granite, and that's also radioactive. But sodium 1 gram of sodium. Spent fuel, reacts core of it, and you stick on 18 exabecquerels, exabecquerel, showing a fission reactor core in its decay form, which is an inconvenient truth. Something is extremely radioactive. But the good side, most of it decays away at 400 years. After 100 years, this is low level waste definition in the UK. But a lot of half-life football. But actually, the first 1 year, it's actually really difficult to maintain. We haven't actually got a solution yet on that sort of level radioactivity. We don't really stick probes in central reactivity, but it survives. So, how do you maintain and look at fusion reactor during operation? Is a major challenge. I'll stop there because I don't want to take over too much time. There's those more challenges. Steel swells. See that one? So you do see steel swells. They're on the, I mean, you've seen how steel swells. One thing we work with quite often, there's only one picture I'll show you. So this is a real good picture. This is from the 1760s. This is discovered in June. So this is a bar 314, 316, stainless steel, standard stainless steel off the market. It was made out of all the reactors, fuel pads. And then you stick it here. This is about going to about a year's worth of time in a reactor core. I mean, you can see the difference. It's physically schooling. So it's near impossible design for that. Think of fail on the programs, yeah, pull them out. So this is unique to SMD stainless steel. So we know this, so we just don't use it. But that's one thing which does. We found the British found that first in the fast reactor. So we just have decommissioned part. Fusion has these issues to deal with. I'll leave it there on a positive note. Any questions? Yes.
Yeah. So how do you think that the editing announcement will affect itself using I think it will or should.
Country dependent. So take the UK.
UK, sorry.
In the UK, so we're blessed by wind, blessed by solar, and we are tidal. We have a lot of the geology around the UK is actually very favourable for the UK. The power will always be around. We're ultimately going to get rid of it for now. So I reckon it'll be more of that. And the reality is that it's very hard for politicians to commit to anything practical. So we're not going to do the factory. I can't see that. Not practically, but just physically. So I think it'll be more of that. Where fusion fits into that, I think it's huge. I don't think we actually still know, even though what the conference today or Saturday tomorrow. That's how it will sound. But company do work on the technical challenges of materials. Some of the things, these are very hard to solve. It's very hard to see what's on the other side. Doesn't mean it's just technical challenges. Yes.
If there are so many material, physical, and chemical challenges, what's the incentive for your company to pursue it?
Oh, most of the programs. The thing about materials, so I'll go back to the picture of it's all about. I'll take this top of the energy, I'll take the of vision. This thing is not doing fusion, it's just doing plastics, which are like fusion. So this is just made out of just normal material off the market. And they can look like particles. So a lot of this is actually testing plastic physics, testing diagnostics, and testing how to heat systems. When you actually put it all together and try to go to the power regime, you then force an actual neutrons. There's all of the neutrons. So about how many, and it's the interval of the neutron, which is the important part. But the interval depends on time. The time one we work on are years, but no one's operating reactor for years. We're nowhere near them. But we have a very good idea of what it's going to look like material perspective, but there isn't any motivation incentive for investors to kind of work on these issues today because you're not going to see this return. So it's more a case of choosing the battles, which is the most important thing today. The most important thing today I see devices like this, testing them, having experience. Where my company fits in, we have some IP in materials, and we have a lot of these companies that understand how to get to the end point. It's not just materials, there's other things that I've spoken about. A lot of them just don't look right. So I've said all of it. So far, we're the only very few fusion companies making money. Exception. Everyone's actually making real money on fusion companies. We want a job until there's an abundance of work to do. Yes.
The question I've got is the all of the plasmas now pretty much sorted out. These materials problems really attractive. This may be one of these very smaller reactors that we get on prototype plastic.
That's the implied assumption. The implied assumption is because I can make it smaller, HGS magnets can make that reactor smaller, you can have a higher magnetic field in a small space, and that's what you need in defining plasmas. The implicit assumption is that equals cheaper. What it actually does in terms of it's a square meter problem. So if you shrink your reactor first wall size, that actually if you sum the meters squared around it, but have the same power output, you end up having a higher temperature in the wall, higher neutron loads. So you end up having you accelerate problems which the larger scale fusion doesn't see in years of time. So it makes some of your sort of engineering problems a bit more acute. But there is the implied assumption, and you hear it between the companies. I understand why it exists. Smaller equals cheaper equals faster. There's no evidence that's actually true, but that's the assumption.
This is a very similar question to which I wanted to ask because kind of from my impression, the thing about the nuclear fusion, like and its usage like the power plants is finding a soft spot between like scaling the project up to this moment that it doesn't cost too much trouble. Do you have like any estimates of the like output of this kind of power plant at this point, like order of magnitude, like what there was, because I've seen there was like the only figure that was in Europe was like slides was something like 200 megawatts. But it's
Oh yeah, that was yeah.
yes, but it's certainly too little to power and
Yeah,
be
it's really
considered.
megawatts. Yeah. Is it better to have 10 100 megawatt reactors than 1 gigawatt reactor? For fusion, I would probably say on the front of it 10 100 megawatts, only because I don't think you can run 1 gigawatt plant for availability over 80%. So just because there are so many, there's so many challenges that we just don't have information on to give the reliability. So reliability is really important in power output. So nuclear power is at 99.7% reliability, it's always on, and it's for the maintenance. Same with wind, obviously, very depending on whether it's availability about 40% for the entire calendar year. Solar is generally follows the sun. Fusion, that's one of the biggest question marks. It's how long can you stay up for before the shutdown maintenance don't happen to it. So I think if you take the 1 gigawatt scale, which is kind of like meter size, that's what pretty much most passive physicists will tell you. If that shuts off for 6 months to 1 year for maintenance, you've got the money. So I don't think it's a viable business model. It touches on that. Whereas if you have, this is the idea of CPS taking, right? And all the other power fusion companies, there were 10 small ones that net out. So then you have a rotation between them. So one operates for 6 months, one shut down. It's the same with small modular reactors for fission. The same concept, just to have that sort of. I get that.
Still not that much.
Not a lot, is it?
Like, because for example, like Poland, I think the energy consumption of Poland is energy need is 45 gigawatts. Correct me if I'm wrong. I messed up the scale.
Without some kind of.
So you need 35 power plants like this. Or
Yeah, when you think about the scale.
so in Europe, like you would imagine, you need something like 10 times this, so for 450 power plants.
I mean, it's about 450, 440 pressure nuclear reactors around the world. It's not unfeasible. Well, it's not really I can do the first one. But I mean, today, for example, at the Fusion 20 conference, it happens to be today, so they were talking about 1,000. People were talking about 1,000 rolled out. That's pretty ambitious. There are some significant supply chain problems of digging up raw material. It's about 1,000. Gas tungsten, there was 3,600 tons of tungsten, right? Sounds a lot. Actually, when you work it out, that's half the year production of tungsten by just one reactor. And we're going to have to replace the tungsten, by the way. I mentioned that. It falls apart, so we have to replace it. 2, 3, 4 years, we don't really know exactly how long. So you replace the entire 3,600 tons to replace. And that waste is mainly waste. We haven't got a plan to recycle this. It's now not tungsten, it's really tungsten. So what do you do with that? So yeah, it's just one of the many other materials that's brilliant and it's different than that, which is also an issue. That's a conversation for another day. We also work on supply chain. Yes.
These small fusion, how big and heavy are they actually?
These?
Yeah, small ones. If they end up working, what's the size thing we think of how much they work? Right, so more stroke transportable.
I don't think I thought that far ahead, but yes, I would say go either on barges or road transport, possibly train.
So you could make them centrally.
Yeah, you would assemble them as well. I mean, it's not a good example, but each is all sourced together by multiple, that's really big. But the idea that they're being built piece by piece, you don't have one single steel structure. You're going to have to build it because it's so complex, it's shaped in sizes, you can't do it. And don't say it's really pretty. That's not nice.
Just a technical question. If these things just stop working, how much heat is stored in that plasma?
The energy, it's going to be megajoules, it's megajoules scale.
Okay, but so quite a lot,
It's not an enormous amount. It all depends on how you control the descent of dissipating it. So you can control the descent of the plasma on onto the water. That's what's done all the time. If you lose control, which is called disruption, well, the plasma essentially collapses and ejects into some location on the balls. Jet's done it. Has happened to jet. It melts the tile, it strips up the tile off basically. But jet's quite small, it doesn't have that much energy. What it did do is most of the jet was raised off the floor. They were designed to do this about that far. And a lot of the jet was enormous. It caused an earthquake. All the monsters around Oxfordshire went off to cause an earthquake about 2 Richter scale. They now coordinate when the jet force happens. So people don't think there's an actual earthquake. But if you go to the ETA scale, disruption, if you ask an ETA plasma control engineer, physicist, and you ask what's your mitigation for a disruption, no, say that ETA doesn't have a disruption. Okay, but what happens if there is a disruption? You lose control of the plasma. There's a chance. But the real answer is rip a hole through the wall, rip a hole through the back of the vessel, and it may rise off the whole reactor. So what was that $1 billion? The stored energy can actually rip holes through, and then you have things behind there which doesn't want to come out, liquid metals, water. You have conventional explosions. Let's get too expensive, but yeah, that's the access to now is a thing that we don't really think about. Anyway, that's the state of fusion, by the way. In a positive way, there's lots of things that happen. There's a lot of momentum. There's a lot of hype, I would say. There's a lot of hype. There's a lot of money. There's a lot of rich people. I asked the question the other day, so who's investing? I'm like, there's a possibility.
Well, you've got all these different technologies coming in.
Yeah.
Super some of them not going to work. Now, do you have any ideas for proposal?
You want investment?
Yeah.
Is that what you're looking for? Possible. Some we actually do, but we have one guess. This is there's two camps. I think of two camps in fusion. You've got I mentioned that the barriers to physics. So the barrier in the sense of like we understand how to do talk about fusion. All we need to do is an engineering problem. We know how to get to point B, which is just electricity in the grid. But the jobs to do that are really difficult in engineering. That's what we're talking about. And that's where magnet finds. We know how to find classes, we know how to fuse them, we know how to make DT fusion, we know how to do all that. Sustaining it for a long time, so we haven't been able to do more. Going from there to imagining a reactor that actually somehow make electricity, that jump, that feat is enormous in engineering skills. Now, a lot of these companies, so CT Fusion, Princeton, Helium, that Hydrojet, first slide, Marvel, there's others. They don't do talking, they don't do any of that. I mean, they do very different ways of finding. Now, the barriers to physics and actually making that to cause more fusion, more power than it. It's very high, it's unproven, we haven't really got there yet. But the cost of doing those experiments are tens of millions. It's not a billion. So you can actually get to it. So that's the bit of those business models. Now, I wish I could get to the Sam Energy, the best one for demonstrating what their technology is. It's like a bathtub, essentially, a very fancy bathtub. And you have essentially a plasma which fuel on the end of it, essentially a copper rod, which conducts electricity. Very flow high, around prices of the world reservoirs of fuel. Of course, the idea of fusion, neutrons go into space, right? In that space, it would be essentially a ton of liquid. That produces tritium, and then you cycle it around. And you end up having a very low pressured hot region, which is maybe 4 meters diameter, which is the same sort of size of the pressure of the reactor. So well known how to do that, but it's not pressurized, it's at atmospheric pressure. And it flows around that heat exchanger, and you can see the entry to just the quick easy stuff you can tell that. Because a very 18th century, 19th century technology. But the barriers of physics are so high. But then it's cheap to do. So they can get investment. And then you touch on the billionaires and state funding and things. There gets a bit of a different business model. Whereas the guys over here, it's like dogmatic approach, very confident in physics, jump to the commercial path. I think it's a much greater jump, but there's less risk to do so in high tech. So if you actually which one's down, you know, if you took the purely risk approach, you would choose companies to be in climate, but you shouldn't compare all these companies to achieve for that's my opinion. I have no insight. So I'm going to take that as advice at all. Is it what you thought it was? Or future? And I have opinions about the future. Is it different? Different, yeah. There's a lot of jobs, but the hardest part is finding qualified people to help these companies. Again, talking about know them very well. We started working with them when there were 20 people. They're now to 200, and they can't recruit quickly.
Maybe you can
Which
leave
is good, by the way.
to the 9 group and we can have for group, which I guess we are overdue.
Yeah. Thank you again for coming. And thank you to the
Thank you very much.
Thank you.